As I said earlier on, always we need the two signals, which is our message signal m of t, which is equal to am cos omega mt, and our carrier signal c of t equal to ac cos omega ct. In having this, the input, which is the adder v1, is equal to m of t plus c of t. And as I said earlier on, that the inputs, the message signal can be of any signal, therefore we release it like that, and we bring the actual equation in when necessary. And therefore we are going to have our AC cos omega ct. So this is our equation 1. At the conducting stage, C of t is greater than 0, and therefore the diode is on state and it behave, the switch is closed, or it behave a switch. At the point where C of t, our input signal, is less than 0, is at the off state, and therefore our switch, it closed. So now that we are going to work on the conducting stage, we assume that our C of t is greater than 0, and therefore we can come into conclusion that our V1 equal to V2. And as I was saying earlier, our modulator will pick the input and multiply it by a train of pulse and give us the output. In that case, it has modulated it. So V2 equal to V1 multiplied by the train of pulse. V1 multiplied by the train of pulse. So basically, this is what we have for the output of the diode. And now let's move on to the simplification. The train of pulse that I illustrated for you here, J of t, can be obtained using the Fourier series. And this class, you can refer to your signals and systems class. You did some Fourier series. You can use the general form of the Fourier series, 1 over 2 plus 2 over pi, the summation of n equal to 1 to infinity, and then negative 1 to the power n minus 1 over 2n minus 1 cos 2n minus 1. Then we can say omega ct. Excuse me. Since this is not our focus, the train of pulse has been simplified using the Fourier series, and therefore we are going to go by the final equation. So if you want any proof of how this train of pulse came about, you can use the Fourier series for the proof. And therefore the final equation for the Fourier series is going to be 1 over 2 plus 2 over pi cos omega ct. So this is the Fourier series generation for the train of pulse. Now that we have the Fourier series for the train of pulse, we will then have our output as V2 equal to V1 dot G of t. Where is our V1? Our V1 is our message plus the carrier, and therefore V2 equal to M of t plus AC cos omega ct, and then multiply by 1 over 2 plus 2 over pi cos omega ct. Now the rest will be algebra. In simplifying this, m of t multiplied by this one is going to give us m of t over 2 plus 2m of t over pi, and then cos omega ct plus AC over 2 cos omega ct, and then plus 2AC over pi cos squared omega ct. This is our output equation after the diode has converted it into a train of pulse by multiplying the inputs by the train of pulse. Now we have this as an output of our diode. You can see that there have been a lot of harmonics or extra terms being generated apart from the original function we placed in for modulation. And for that matter, we need to pass the whole output into a bandpass filter. So in passing to a bandpass filter, this is our V2, and then we are going to get our final S of T. So in passing this through our bandpass filter, this is of a lower frequency. Even the message that we place in as an input has been divided by 2, and therefore the bandpass filter will get it out. Looking at the second one, it has our message, it also has our carrier, so we leave it. The third one has our carrier and then the carrier frequency, which is being used to carry the message, we leave it. The third one, which is AC square here, the third one has the square of the cos function, and therefore it will be having a higher frequency, and therefore our bandpass filter will attenuate it. So at the end of the day, we are going to get our final output V2 to be equal to S of T after passing it through the bandpass filter, and the result is going to be 2m of T over pi cos omega ct plus AC over 2 cos omega ct. This is what we have. So aside that, we can do a little bit of algebra to factorize some things out. So we can see that we have our cos omega ct out. We get our AC over 2 plus 2m of t over pi. At the end of the day, we can say that we can still bring some parameters out over 2 cos omega ct, and then into bracket 1 plus, you know there's no 2 here, so the top one is going to be 4 m of t over pi. When I multiply this one 2, it will cancel this one out and we get 2 again. So in this way, we can see that our AC over 2 here, it's an amplitude of a carrier. And then we can also see that our 4 over pi, and remember that there's no AC here to I forgot to bring this one here, AC is also going to be equal to M, which is our modulation index. So in this way, we can write the final output equation to be equal to AC into bracket 1 plus, in case we are representing this one by K naught, which is equal to M, we are going to get K naught M of T cos omega ct. This is the same as the equation that we have already worked on in my previous videos, and this is the switching method of generating an AM wave. So in conclusion, for the switching method of the switching modulator, I would like to summarize everything here. So we get our 2 signals as usual, which is my M of T and my C of T, my message and my carrier. We pass it through a diode. This diode will convert it into a train of pulse by multiplying it by the train of pulse signal, and due to the nonlinear nature of the diode, there will be an integral multiple of the fundamental frequencies, the harmonics being introduced into the system. And for that matter, we need to filter out all the unwanted parts. To do that, we pass the whole output of the diode into a bandpass filter to filter out the unwanted part to get our original modulated signal, which is S of T. So in conclusion, all message signals lies in the frequency range of 20 Hz to 20 kilohertz. So in order to transmit any message in the form of in between the range of these frequencies, there should be a modulation, and therefore we need a carrier signal to carry this information for us. So if you are doing this and you are varying the amplitude of the carrier signal with respect to the amplitude of the message signal, this is what we call AM modulation. and this is the modulation type that we have been generating the general AM wave for it using the square law method and the switching characteristics method. The same applies to the frequency modulation. When you are varying the frequency of the carrier signal with respect to the message signal, you are doing frequency modulation, and the same thing applies to the wave, the phase. When you are varying the phase, this is called the phase modulation. So thank you for watching, and in my next tutorials I'm going to talk about how you are going to use this general formula by expanding it in such a way that all the necessary components of the AM wave or modulated wave will come out for you to see the various bands of the AM waves. So thank you for watching, and see you in my next video.